Okay, let's begin by deriving Kepler's third law in this lecture. As you may recall, from angular momentum conservation, we concluded the Kepler's second law, which says that the radius vector sweeps equal areas in equal times. Okay, so that is what was second law, and let me write it down. Angular momentum implies that dA over dt is a constant, okay, and that turned out to be L over 2 mu. Okay, this is what your second law is. Now if let's say we are looking at ellipse, okay, elliptical orbits, then if it takes a time t, which I write like this, a capital T, okay, to complete one orbit, okay, then in the time t, the radius vector is going to sweep an area A, which is equal to the area of ellipse, that is pi times A times B. Okay, A and B are semi-minor and semi-major axes. Okay, that's the area of ellipse. So in this time t, this much of area will be covered, and if you use your second law here and integrate this equation, you will get A is equal to, when I'm integrating this one, and I'm just writing what value it is, so L over 2 mu times t. Okay, I've just done an integral. Now you recall how semi-major axis, semi-minor axis is related to semi-major axis, and the relation, if you recall, is this. Okay, and if you substitute the values, you will get A square root of A L square over mu k in the square root. Okay, now if you substitute A is anyway here, if you substitute B in this expression, okay, you'll get the following. You will get that T is equal to 2 pi. The algebra is simple. You have to just plug in few quantities here. A to the 3/2 mu over k in the square root. Okay, which means your t square, if you square both sides, 2 pi square, then you have a mu over k times A cube. Okay, which says that time period square is equal to a constant times semi-major axis cube. And this is your third law. Okay, so for a given given two-body system, the mu is fixed, and so this piece is truly a constant, and this is how your time periods are related to semi-major axis cubes, and that's what your third law is. Okay, next I want to talk about a special vector that is conserved when you are looking at Kepler problem, and this is called Laplace-Runge-Lenz vector, and that's what I'm going to look at now. So we will talk about Laplace Runge Lenz vector. So out of the momentum, angular momentum, and the radial vector, the radius vector, which gives the location of the particle. Okay, let's define a quantity which I denote by A as follows. So I take the cross product of the momentum of the particle mu, wherever it is, with the angular momentum which is conserved. Okay, this is a cross product, and from this you subtract mu k times the unit vector, unit radius vector. Okay, so I've divided by r, which makes this quantity a unit vector. Okay, a small exercise, trivial one basically. Argue that A lies in the plane of motion. Okay, so you should argue that A, the vector A, is a vector which is in the plane in which the particle is moving. Okay, that's a fairly simple exercise. Now I want to show that this is a conserved quantity, meaning I want to show that if I take the time derivative of A, I will get 0. Okay, that's what I want to show. So let's calculate the derivative. So I have P cross L. So first P dot cross L plus P cross L dot. Okay, that's good. Minus mu k. I have dr over d over dt of this. Okay, I'll save it for later. Now this is 0 immediately. Why? Well, because L is conserved, so dl over dt is 0, and that is what is here. You have L dot, so that is 0, so this is gone. And let us now look at these two terms, 1 and 2. Okay, so term 1 is the following. So I have P dot cross L. Now P dot is the force. Okay, the rate of change of angular momentum is force, and our force is minus k over r square in the radial direction, which I will write as minus k over r cube, and I write r here, which makes it go as 1 over r square, and the direction is captured correctly here. So you have P dot. Now let's multiply with this or cross with this angular momentum, and angular momentum is r cross P, which I write as r cross P would be mu r dot. Okay, that's good. This is same as maybe I will leave it as an exercise. So you have here r cross r dot. Okay, and this I'll just write down the result. It's simple algebra you can do. So the result will be minus mu k. Okay, then you have r dot. So there is no vector here. This is just r dot, the radial velocity, over r square times r vector minus r dot over r. It should be not very difficult to obtain. Then the term number 2, you can check it will, it's simple derivative. So you have you will get minus mu k. Okay, and then you will have minus r dot over r square times r vector plus 1 over r dot. Okay, now let's see what is sum of 1 and 2. So you have minus mu k, these are common here in both. So you have r dot over r square r dot over r square r with a minus sign, so that cancels against this one. And similarly the second one also cancels. So 1 plus 2 is 0, which means dA over dt is also 0. Okay, which would imply that A is a conserved vector. Okay, and this is what a Laplace-Runge-Lenz vector is. Now this is a conserved quantity, so should you be expecting a symmetry which will lead to this conservation? Okay, I will leave you with that thought about this. Now what you can ask about this vector A? Now you may think, okay, what's the magnitude of this vector A and where is this vector located? Of course it's going to be fixed in space and not change with time because this is conserved. And you would like to know where that vector A is located and what's its length. Okay, that's what we want to take up next. Okay, so it will be very useful to mark all the quantities which are related to ellipse before I calculate the magnitude and direction of that Laplace-Runge-Lenz vector. Okay, so I have drawn an ellipse here, and let me just fill some of the details. Here is the focus. Okay, this point is called perihelion. Okay, so some nomenclature I want to throw. Perihelion. This point, the opposite point which is furthest away from the focus, is called aphelion. Okay, let me also write down the equation which we wrote some time back. This is A times 1 minus epsilon square. Epsilon is the eccentricity, and you have 1 plus epsilon cos of theta. This length is from here to here. The place where theta is pi by 2 is A times 1 minus epsilon square. That is correct. Okay, this is the closest distance, and this is A times 1 minus epsilon, and from the center of the ellipse to the focus is A times epsilon. Let me denote that also by these. Okay, okay, perfect. And this the rectangle which you see here is 2A from here to there, and this length is 2B from here to there. Okay, now we want to know the magnitude of A. So you can choose any point in the orbit and try to calculate the vector A. So you find out what is the momentum at that point. Let's say you choose the point to be here. Okay, so you should find out what is momentum there, and angular momentum is anyway fixed, so there is nothing to get from the orbit. And then you find out what is the R for that point, so this point. And of course it will be best if you choose this point to calculate A. And it does not matter where you calculate because it's going to be a constant, right? It's not going to change. So let's look at this point and evaluate A at this point. So it's here. So maybe I can give expression on the next page. Okay. So it is easiest to determine A by looking at by evaluating it at the perihelion. Okay, so let's do that. Exercise number 1, trivial, almost trivial. P cross L. Okay, we want to evaluate this as at RP. So by P I mean perihelion. Okay, so this is this length from focus to perihelion I am calling RP, which is A1 minus epsilon. Okay, please show that this is equal to the following: mu k 1 plus epsilon. K is the thing which appears in the potential and mu is your reduced mass. Epsilon is the eccentricity times Rp over Rp. Okay, so that is what you should get, and maybe I should emphasize that Rp is A1 minus epsilon. This is Rp. Okay. Okay. So that is Rp. I just removed because I didn't want to clutter this page. And all you will need to really use is that P and L, so the momentum and the angular momentum at perihelion would be having 90 degrees. See here, the particle would be going in this direction. Okay, and angular momentum is anyway, I mean, sorry, angular momentum is anyway perpendicular to R, so and P correspondingly. So that is not the point. What I wanted to say was at this point, the momentum is also perpendicular to the radial direction. So this vector and this momentum, they will be having 90 degree. Okay, for the same is not true at any other point. I mean, for example, here. Okay, or is it? Okay, anyhow, at this point it is true. Probably for ellipse it may not be true. I'll think about it later. So that is one thing you please show, and once you have done that, our vector A is immediately available to us. So A would be mu k times 1 plus epsilon Rp over R, that's the first term, minus mu k Rp over R. Okay, and calculating that is also I mean, it's quite easy. There is not much, and with that you will get the following. So you have mu k, and 1 plus epsilon minus 1 will give you epsilon, and then you have Rp over R, which is just the unit vector in the direction of perihelion. Okay, so that's the That's the Laplace-Runge-Lenz vector. Okay, so I'll stop this video here and we'll continue further in the next video.